Hello everyone, my name is Sogol and I'm a PhD student at University of Wisconsin-Madison. The work that I want to present today is about comparison of real and synthetic network models of the Western United States with respect to neorealism measures. This work has been done as a part of ARPAE Grid Data Project. The history of synthetic grids goes back at least to 1970s in the APRI project, where they tried to generate synthetic cases to be used in power system studies. In the past decade, particularly in the ARPAE Grid Data Project, we tried to generate synthetic cases on the footprint of US electrical grid. The motivation in that project was to use these synthetic cases to evaluate the performance of different optimal power flow algorithms. The full AC optimal power flow problem in the format that we know nowadays was first introduced in 1962 by Carpentier. And since the beginning, due to the nonlinearity and non-convexity of its constraint, it was recognized as a hard problem to solve. Ever since, scientists are trying to propose different solution algorithms to solve optimal power flow problem, for instance, different convex relaxations. And this is still an open topic of research. Whenever a new method is proposed, in order to make sure of its performance and accuracy, it needs to be tested on a real network model. However, real power system data is confidential and non-public, meaning not all the scientists have access to such data. And this raised the need for realistic synthetic power system models which are publicly available, and that was our motivation in the Grid Data Project to generate those cases. We believe these cases are realistic, but how do we show that? There are different realism measures that can be used to evaluate the realism of a synthetic case. The first category addresses the electrical characteristic of the power system components, for instance, number of buses, generators, different voltage level, characteristic of line and transformers, and so on. And synthetic cases usually are designed in a way that they comply well with the measures in this category. The second category are topological measures. To name a few, in this category, we can have different kind of centralities, Fiedler Vector Partitioning, associativity, and so on. The third category addresses both topology of the network and the electrical characteristic of power system component. For instance, in this category, we can have tier values or singular value decomposition of power flow Jacobian. In this study, from the first category, we chose the line length. From the second category, we chose the node degree centrality, eigencentrality, Fiedler Vector Partitioning, and a spectrum of the normalized Laplacian. And in the last category, we chose the tier values and a singular value decomposition of the power flow Jacobi. And among all of that, FVP, SNL, tier, and SVJ are the new realism measure of this study. The test cases that we used are two synthetic cases on the footprint of the Western United States. ActiveSG is from Texas A&M University, and WI 121 gigawatt is from University of Wisconsin-Madison. And we compared these two synthetic cases to the actual model of the Western United States, which we know as WEC. As you see in the table, they differ in terms of number of buses, branches, and generator. And before we analyze these cases, there are a few things that we'd better to know about these cases. For instance, in the WEC model, there are portions of Canada and Mexico electrical grid which are removed for the purpose of this study. And WEC includes elements in subtransmission and distribution voltage levels. And there are around 3,000 lines in below 69 kV in the WEC model. In ActiveSG, load is aggregated to realistically sized transmission substations. There is no subtransmission system. Generators are connected to the network via a step-up transformer, and there are no transmission line in below 69 kV. In WI model, there is a substation for every census tract that the load was measured at. Generator units are connected to the network directly without any step-up transformer, and there is no transmission line in below 69 kV. In order to have a fair comparison with respect to topological measure, due to the details that I explained in the previous slides, for instance, there are subtransmission and distribution part in the WEC model, and WI actually models some of those details at 69 kV. We have removed the pendants or radial lines from the different networks that we have, and we rolled up the network in order to have the minimum node degree equal to 2. With this strategy, we could actually generate the mesh part of the network, which mostly correspond to the transmission side of the network. we use this mesh network for the topological measures, and for the rest of the measures we use the original network models that we had. Let's start from the topological measures. The first one is node degree centrality. This is the simplest centrality that determines how strong a node is connected to the rest of the graph. The node's degree centrality is the number of edges incident to one node. We have calculated this measure for the three cases. I should mention that the maximum node degree in the VEC model is 14, in the active SG is 13, and in WI is 29. The presence of such a hub node in WI model is notable because this is not a behavior which normally is seen in real power systems. And we have derived some stats for this measure, for instance, mean, standard deviation, and median, and you can see it in the below table. Comparing these values and the histogram that we got for the data, we can conclude that active SG show more realistic behavior with respect to this measure compared to WI. Another centrality is eigenvector centrality. It is different from node degree centrality in a way that it incorporates the centrality of the adjacent nodes. For instance, in the two simple graphs that I have here, the middle nodes have similar node degrees. However, the node on the right have higher eigencentrality since it is connected to the nodes with higher node degrees. The eigencentrality of the nodes in a graph are equal to the components of the dominant eigenvector of the adjacency matrix. The adjacency matrix is a square matrix that shows the connectivity of a graph. If two nodes I and j are connected to each other, the corresponding component is going to be equal to 1 in the adjacency matrix, otherwise it's going to be equal to 0. We have calculated this value for the three test cases, and here in the histogram we have plotted the values in the log2 scales. As you see, VEC model and active SG have more or less the similar histogram with a little bit shift in mean. However, WI has a very narrow histogram compared to what is seen in VEC. Comparing the values that we got, the different stats that we got for these measures, we can conclude that active SG follows the behavior of the VEC model with respect to this measure more closely than WI. The other topological measure is Fiedler Vector Partitioning. Fiedler Vector is the eigenvector that corresponds to the second smallest eigenvalue of the graph Laplacian. It determines critical edges and nodes in the graph, and in order to calculate that, first we need to calculate the Laplacian, and we need for that we need to have the incidence matrix of the graph. Having the incidence matrix multiplied by its transpose, we can calculate the Laplacian of the graph. The second smallest eigenvalue of the graph Laplacian is called Algebraic Connectivity or Fiedler value, and if the graph is disconnected, it's going to be equal to 0. Otherwise, if the graph is connected, it's going to be greater than 0. Comparing the components of Fiedler vector with respect to this measure doesn't give us any information. What we can compare is to partition the networks that we have with respect to the sign of the Fiedler vector component to two different blocks and compare the size of those blocks, and we can compare the number of lines present in the cut and the Fiedler value. Having these values calculated for the three networks, we can conclude that VEC and WI model more or less have similar block size. However, active SG has a different block size than what is seen in the VEC model. The number of lines present in the cuts in the two synthetic cases is close to what is seen in VEC, and WI model has closer Fiedler value to what is seen in VEC. Therefore, we can conclude that with respect to this measure, WI shows more realistic behavior. The last topological measure is a spectrum of the normalized Laplacian. This is the set of eigenvalues of the normalized Laplacian. We can calculate the normalized Laplacian of the graph using the Laplacian that we have for the Fiedler Vector Partitioning. Having the Laplacian multiplied by 1 over the square root of diagonal degree matrix, we can derive the normalized Laplacian. The eigenvalues of the normalized Laplacian are between 0 and 2. The number of 0 eigenvalues indicates the number of islands in the network. The number of 2 eigenvalues indicate the number of bipartites. We have calculated this measure for the three test cases. As you see from the stats that we got for this measure, we can conclude that active SG follows the behavior of the VEC model more closely. However, in the histogram that you can see that in the VEC model, we have two spikes around 1 and 1/2. In the active SG model, we have one spike around 1, but we do not have any spike around 1.5, and in the WI model, there is no spikes. This got our attention, and we have calculated the number of repeated eigenvalues in the three models. We realize that we have 120 eigenvalues which are repeated in total 318 times. ActiveSG have 7 eigenvalues repeated 16 times, and WI model have 2 eigenvalues repeated 4 times. And this repeated eigenvalues, which is in the VEC model, does not show up in either of the synthetic cases. The next measure is the line mileage. Since these are synthetic cases, the actual length of the line are not present to us. Therefore, we use the propagation velocity in a lossless transmission line to calculate the lengths of the lines. The propagation velocity in a line is equal to 1 over square root of LC. L and C are per unit length inductance and capacitance of the line. Having these values replaced by per unit reactance and shunt susceptance of the line, we can calculate the length of the line. We have calculated these values for the 3 test cases with respect to different voltage levels. And in the bottom table, you can see the number of lines present at each voltage level. And you see that in the first and last voltage level, we more or less have similar number of lines in the synthetic case as we see in the VEC model. However, comparing the length of the lines with respect to different voltage levels or all together, it is very hard to conclude that which synthetic case show more realistic behavior with respect to this measure, and we can say that neither of the synthetic cases show realistic behavior with respect to line length. The next measure is topological and impedance element ranking, or tier. Tier is a method of ranking of branches in the network to identify their importance in the bulk power system. The idea behind that is when the branch gets congested, what would be the impact of it on the changes of LMP values. To understand it a bit better, let's start from a DC optimal power flow problem. The objective function is to minimize the generation costs subject to power balance equations. And since we calculate the tier value when the branch is congested, the last constraint indicates that the flow in the line is at its max limit. We can reformulate that as the infimum of the Lagrange function, and in the Lagrange function, the dual variables have physical interpretation. Lambda indicates the nodal prices and mu indicates the shadow price of the line. Due to the optimality condition, if we equate the derivative of the Lagrange function with respect to theta to 0, we can derive a relation between lambda and mu variables. The changes in the lambda with respect to the changes in mu is going to be equal to the -1 BF tilde transpose multiplied by B tilde inverse. Tilde indicates that we have removed the column and row corresponding to the reference bus from these matrices. And since we need a scalar to define the importance of the line, the tier value is defined as the standard deviation of the components that corresponds to the generator buses. We have calculated this value for the 3 test cases. As you see in the histogram of the data, there are second spikes in VEC and active SG model. These spikes correspond to the generator step-up transformers. However, in the WI model, the second spike is missing because, as I explained, there is no step-up transformers in the WI model. Comparing the stats that we got for this measure, we can conclude that the active SG models show more realistic behavior with respect to this measure. The last measure is singular value decomposition of the power flow Jacobi. We have calculated the singular values of the DC power flow Jacobi for this measure. It can be computationally expensive for large cases. However, the computation burden can be managed by partitioning techniques. We have calculated this measure for the 3 test cases. As you see in the histogram, if we were to actually fit a distribution to this histogram, we can use a one-peak Gaussian distribution for WI model and the VEC model. However, for the active SG model, we need a 2-peak Gaussian distribution. So they are different from what is seen in the VEC model. And from the stats that we got for this measure, since they differ greatly, both synthetic cases in the value of the stats compared to the VEC model, we can conclude that neither of the synthetic cases show realistic behavior with respect to this measure. To conclude, we have actually compared two synthetic grids on the footprint of the electrical grid of the Western United States to the actual model of the same area. Realism measures were selected from 3 different categories. Even though each synthetic case compares well to the actual model with respect to some of the measures, neither matches the actual model with respect to all the measures. And we should mention that close alignment with respect to all the measures is not a necessary condition for a synthetic case to be realistic. And since most of these measures have low computation burden, they can be used in order to tune synthetic grid creation algorithm as future work. Thank you for your attention.